let's take a look at some of the properties of definite integrals. Our first example is the integral from a to a of f of x dx. Notice that the lower limit of integration is a, and the upper limit of integration is also a. That means we are integrating this function over an interval from a to a. And so imagine, if you will, having a function, maybe something that looks like this, and wanting to find the area under the curve on the interval from a to a. Well, if we think in terms of representative rectangles, similar to those used with Riemann sums, we can see that the base of this rectangle, because we're going from a to a, would be 0. There is no length to that base. So for that reason, and base times height being the area of one of those rectangles, stop pulling rectangles in. Welcome. Let's take a look at some of the properties of definite integrals. Our first example here is the integral from a to a of the function f of x dx. Notice that our lower limit of integration is a, and our upper limit of integration is a, so that tells us that we are integrating this function over the interval from a to a. Now imagine, if you will, a coordinate axis with the graph of some function. Maybe it looks like this function here, and wanting to find the area of under the curve from a to a. Well, looking here, we can recognize that basically we end up with something looking like a line segment. It has no width, and therefore it has no area. So the area under the curve from a to a is 0. Therefore, the integral from a to a is also 0. In our next example, or our next property, we have the integral from a to b of f of x dx and the integral from b to c of f of x dx. So in this case, in the first integral, our lower limit is a and our upper limit is b. So we're integrating over the interval from a to b. And then in the second integral, our lower limit is b and our upper limit is c. So in this case, we are integrating over the interval from b to c. So as we think about this, we can imagine having a coordinate axis with a function, maybe something looking like this, and where we have a, b, and c marked on our x-axis. And when we think about these definite integrals based on the notion of area under the curve, we can see that the integral from a to b of f of x dx would be basically this region, area. And the integral from b to c f of x dx would basically be the region here, its area. So noting that these two areas abut each other, in other words, the areas meet at b, we could just as well think about, rather than doing two separate integrals of the same function but on different intervals, we could just, instead of doing it in two parts, find the area of the entire region. And in this case, our lower limit of integration would be a, and our upper limit of integration would be b. So this would be equal to the integral from a to c of f of x dx. So what we can do when we have the same integrand and we're integrating over two intervals that abut each other, we can join them into a single interval and calculate or evaluate the integral once over that larger interval. So our next property we want to consider is if we have the integral from a to b of f of x dx, and here's our function f of x, and here's a, and here's b. We're working with this idea that the area under this curve on that interval is this definite integral. Well, what would happen if instead of starting at a and integrating to b, I wanted to start at b and integrate towards a? So I want to go in the opposite direction. So I want to integrate in that direction. Well, if you'll recall, when you did Riemann sums and you subdivided these this interval into smaller rectangles, the base of these rectangles was basically your left endpoint, so let's say x sub 1 minus x sub 0, and we would move to the right. Well, instead of doing that, we want to move to the left, and so our rectangles would look something like this, and we would still do x1 minus x0, but in this case that would provide a negative value. So when we integrate and we reverse the interval, so instead of integrating on the interval from a to b, we want to integrate on the interval from b to a. Because we're reversing the direction of that integral, or the direction of that interval, we end up getting the opposite, or the negative, of the integral from b to a. So our next property is the integral of the function k, where k is a constant, over the interval from a to b. So if we were to look at a graph of the area we're trying to characterize here, our function is a constant k, so let's label k there, and because it's constant, that means we have a horizontal line. So there's our function k, and we're wanting to integrate that on an interval from a to b. So we want to find the area under the curve, or the area between that horizontal line k and the x-axis between a and b. Now, in this particular case, I've assumed that k is a positive constant, and therefore this area that we have shaded would be the base of the rectangle times the height. So the base of the rectangle is the distance between a and b, so that would be b minus a, times the height, which is k. Now, I happen to draw this for the case that k is positive. This works just as well for the case where k is negative. When we evaluate a definite integral and we end up with a negative value, this is telling us that there is area under the curve that lies below the x-axis. So if my k was negative and my graph looked something of my function looked like this, and here was a and here is b, and here would be our rectangle we're trying to find the area of, notice that we can still use this idea of base times height. The base of that rectangle would be the distance between a and b, so b minus a, times its height. So my area would still be k times b minus a. It would end up being a negative value, which would then tell us that that area lies below the x-axis. So regardless of whether k is positive or negative, the value of the definite integral from a to b of k dx is b minus a times k. So our next property here is the integral from a to b of k times f of x dx. Now, much in the way we were able to factor coefficients or constants in front out of a derivative and then focus on the meat or the core of that derivative, we can do the same thing here with integrals. So the integral from a to b of k times f of x is k times the integral from a to b of f of x dx. So in much the same way we were able to factor any constants or coefficients out for derivatives, we're going to be able to do the same thing here with definite integrals. Our next property is the integral from a to b of f of x plus or minus g of x. So you'll recall back with derivatives you have a sum and difference rule, which allowed you to separate sums and differences and deal with the two functions separately in terms of finding their derivative. Well, we can do the same thing here with an integral. We can take and look at a sum or difference of functions, and we might make the decision that it might be easier to separate them and focus on the integrating them one at a time. So this is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. The next property we want to consider is where we have a function f of x which is less than or equal to g of x on some interval a to b. Now if we integrate both functions over that same interval, then the integral from a to b of f of x dx will be less than or equal to the integral from a to b of g of x. So if we look at a graph, and here's our a and our b that we're integrating over. So there's our interval, and note that we have this requirement that f of x be less than or equal to g of x. So maybe my f of x looks like this on my over the interval, and maybe my g of x looks like this. Now keep in mind that the requirement was that f be less than or equal to g on the interval from a to b. So if we focus our attention on this interval from a to b, we can see that f of x truly is, the function values are less than the function values for g. Now if we think about the definite integrals associated with both those functions, we can see that we have the integral from a to b of f of x dx here. So integral from a to b f of x dx. And that is, in fact, less than or equal to the integral from a to b of g of x. That integral is going to be much larger, g of x dx. So again, now notice over here on the right, the function f of x becomes greater than the function g of x, but that did not occur on this interval that we were integrating over, so we will disregard that in terms of this property. So remember that this property only applies where you're focused on a specific interval and you know ahead of time that f of x is less than or equal to g of x. Now the last property we want to look at is a means for bounding the definite integral. So imagine, if you will, our coordinate axes. There's x and y, and here's our f of x. And we have an interval from a to b. Try that again. Okay, and we know that the definite integral is basically this area, this region under the curve on that interval. Okay, well, let's see about bounding this. So we're saying that this total area is greater than or equal to the minimum value of f of x on our interval times b minus a. So let's first find that minimum value of f of x on the interval a to b. Well, as I look at my interval from a to b, it looks like this left endpoint, the function value at a happens to be that minimum value. And then what we can do then is we have this rectangle, and that would be this minimum value of f of x on the interval from a to b times, so that would be the height of the rectangle times the base of the rectangle. The distance between a and b would be b minus a. So we can see that the area between this function and the x-axis is certainly larger than the area formed by this minimum value of the function on the interval times the length of the interval. Now let's look at creating an upper bound for our definite integral. And this time, we're going to focus our attentions on the maximum value of the function on the interval. And it appears that the maximum value of this function occurs somewhere right about here. So we would have something like this. That's the maximum value of the function. There's a horizontal line. And we can then look at that maximum value over the entire interval. Over the entire interval from a to b. And when we do that, now what we're doing is we're finding the area of this region, this larger rectangle, and we can see that the area of this larger rectangle does indeed exceed the area under the curve f of x from a to b. We have these extra areas in our new larger rectangle that are not part of the area under f of x on the interval from a to b. You can see that the integral from a to b of f of x dx is bounded below by this rectangle created by the minimum value of the function on the interval, and bounded above by the maximum value of the function on the interval. And so we get this larger rectangle. I hope you find this helpful.